So, furthering our efforts to clearly understand gravitation, we would first of all resort to calculating the mass of the earth, and that was the credit goes to Cavendish, who verified the law of universal gravitation and obtained the value of capital G for the first time. It is a very fascinating experiment of the beautiful mind of an experimentalist, and you can go through that. I will not go into the details because details are very well represented and presented in the books. So Cavendish was given the credit, and it is said that he could weigh the earth. Here the weigh means, because weight and mass, they were confused during those days, so it was basically the determination of the mass of the earth by means of the gravitational force. Now, on the surface of the earth, I have a mass small m, which is being attracted by the earth, and equally the earth is attracted by the mass m. So this gravitational force I can express as capital G m upon Re square. And we can also write that the gravitational force is equal to mg, where g is the so-called acceleration due to gravity, or the gravitational field at the point where the mass m is located. So this will also turn out to be equal to g capital m upon Re square. So from this one we can say that m and m cancels out, and me becomes equal to g into Re squared divided by capital G. Why we can put the value of G, which is determined experimentally. We can put in the value of Re, which is also calculated by other means and believed to be equal to about 6,400 kilometers. Okay, the radius of the earth, divided by G, which is 6.67 into 10 to the power of minus 11, etc., etc. And we put in these values, and when we make the calculations, it turns out to be close to 6 into 10 to the power of 24. So it is, the value is 5.98 into 10 to the power of 24 kilograms. So this is how the mass of the earth was calculated using the Newton's law of gravitation, and the result that was established and was carried out, the experimental experiment, and its outcome gave us the value of capital D, which is 6.67 into 10 to the power of minus 11 Newton per Newton meter square per kilogram square. Anyway, so the next item is, I must discuss with you what is inertial mass and what is gravitational mass, how they are defined. So you know that the inertial mass is defined in the Newton's second law, and I say that the mass of a particle under consideration mi into the acceleration. Okay, F is equal to mi into the acceleration. So that gives the value of mi is equal to F upon the acceleration. Okay, we'll see as to how much it is. Now F is equal to, again we write capital G me upon R square into mg, which I can write as mg multiplied by g. Okay, where g is capital G me upon Re square. Now this gives the gravitational mass obtained in terms of the force, which is measurable, radius of the earth, which is measurable otherwise, which was established, capital G, which was given by Cavendish, and mass of the earth, which was again weighed and determined by Cavendish. He claimed to be the first. So I have Mi and Mg. So I divide Mi by Mg. So what I get, F and F will cancel. Okay. This A is equal to small g. So I write this divided by this gives us the value capital G Me that goes up upon Re square into small g, which is actually the correspondence is with this acceleration. Okay. This is, now you can see capital G, capital Me, capital Re, and G also, which is can be experimentally determined value, known value. All these values are constants, so therefore this is going to be constant. Let us call this constant and say that it is C. Okay, assume that this constant is C, and therefore you can see that Gme upon Re square, and this is also Gme upon Re square. So that will go up. Gme cancels, Re square cancels, and ultimately what we get is 1, which shows that the inertial mass and the gravitational mass close to the surface of the earth, okay, they are both equal. Now, in the tidbits that follow, where we are going to discuss the variation of G with altitude, that is at a height, and going deep inside the earth, when the earth is considered in both cases as a mass of uniform density. So the first thing that I am going to talk to you about is very important, which will be used in the second part when we go deep inside a mine. The gravitational field due to a hollow spherical shell, thin, of uniform thickness and uniform density. Okay. So the mass is evenly distributed all over the thin shell. Okay. This is a very important thing for determining the gravitational field. And therefore the force on any particle of mass m which is located, there are two situations. One is the situation where the point P1 is located outside the spherical shell. At a point P1 I have shown here, and the distance is R1, which is more than the radius of the thin shell. In that case, if we consider this point mass we have considered here, this will I have shown that there is a field, gravitational field over here shown like this, and there could be also a force, that is, if a particle m is there located at the point P1, then there will be a force, and that force will be again, like this case, you can see that this field is radially inwards towards the center of the sphere. One more thing, we can consider for this situation that the entire mass of the thin shell is concentrated at the center of the sphere. So we now have two masses, capital M located here and small m located there, and I can say that the F will be equal to, which I am shown here over here, this is the F, the force, the magnitude of the force will be equal to capital G M into small m upon r1 square, so that the magnitude of the field is equal to capital G m upon r1 square, radial towards the center. Both of them are in the same direction. So I can see that E1 is equal to Gm upon R1 square. Now R1 is either equal to capital R, which is the case of the surface of at the surface, or R1 is greater than capital R, in which case this value is more, and therefore we are dealing with a case which is away. So it's just simple. I have two masses for calculation of the force. I have two masses, and the attractive forces, the force of m on small m or force of small m on capital M, that is given like this. You can say that, of course, in this case there is a force in this direction also. Okay, this same F12 and F21, that has been shown here, and that you know very well. Need not elaborate on that. So in the case of the point under consideration lying outside, having a small mass small m, in that case it's just like the 2 point masses and the Newton's gravitational law, that the force is equal to capital G m1 m2 upon r square, is going to hold without circumstances. Now if the point is here inside anywhere, then what happens is that the shell, the whole shell, if we work out small chunks of masses, then we find that they cancel out each other. The force over here, because of the entire shell that we have, all those forces, sigma of those forces is equal to 0. Sigma of the force is equal to 0. I consider mass over here, then the force is equal to 0. Else we can say that at this point P2, which can be anywhere located inside this, the value of E2, the magnitude of E2 will be equal to 0 always. Okay. So this is one result which we need when we talk about the variation of G. Now let us talk about the variation of G. Variation of G with height, with depth, when we go inside the earth, the variation of G when the earth is located at the point under consideration is at the equator, where the earth bulges, or at the poles where the earth is flattened. So the radius, effective radius or distance of the center of the earth to a point on the poles, opposite poles, which are the gravitational poles, the geographical poles, not the magnetic poles, then of course we can say that the value of G will be smaller at the equator and it will be larger at the poles. And as the latitude keeps on increasing, so a change will be obtained. We can also work it out, but there is no occasion in class 11, 12 to do that. So we can see the variation of value of G with the latitude, the longitude, etc. So we map the values of small g or the gravitational field all over the surface of the earth, and we find very interesting result is, all of you know that water flows from higher levels to lower levels. Higher level to lower levels. But there are patches on the earth that the water flows from lower level to a higher level. And that is because of the variation of the small g or the gravitational field which is associated at that point. So let us take the easiest of the things which we have also done in last lecture for a certain height, and we took that height to be equal to r by 2. Okay. Now, the value of g at the height h I can write as equal to capital G me upon r plus h whole square. In that case, h was quite comparable to r. We have to do the calculations, what percentage and this and that. So I can write capital G me upon, I take r out, so this will be I plus h upon r whole square. I'm sorry, 1 plus h upon r whole square. Now, this quantity I can write as small g. Okay, transfer here, small g into 1 plus h upon r raised to the power of minus 2, because it is in the denominator, in the numerator minus 2. Okay. Now we consider that this h is small compared to the value of r. H is very, very small as compared to the value of r. Okay, maybe a few kilometers, a few tenths of kilometers, because already the radius of the earth is 6400 kilometers. It's a very large number as compared to kilometers. So now we can use in such a case the results of the binomial theorem, where we take the first two terms of the expansion, binomial expansion, and when we do so, 1 plus minus x raised to the power of n, this n could be positive, could be negative, but x got to be very, very small as compared to 1. In that case, the binomial approximation is that we get this value as 1 plus minus nx. When I apply this result, when I apply the result that we have, we get the value of gh equal to g 1 minus 2h upon r. Next we see as to what is going to happen to the case of when we go inside a mine. Okay, that will be a very interesting case, and it's our level also. So the next item, which is an interesting calculation, I have a perfectly spherical earth of uniform density, which is rho kilograms per meter cube, and there is a point r, a mass which is at a distance small r, which is equal to r minus d from the center of the earth, where otherwise the total mass of the system would have concentrated. So now let us see that in the case of a sphere, the volume of a sphere is 4 by 3 pi r cube, where r is radius. So we can write the volume of the earth as equal to 4 by 3 pi r cube, so that I can write this rho as equal to, rho is equal to the mass of the earth divided by 4 by 3 pi r cube, which I am going to use this result later on. Okay, but anyway, mass of the earth m is equal to 4 by 3 pi r cube into rho. From here I get this relation, rho is equal to capital M upon 4 by 3 pi r cube. Now as per our discussions today itself, that if there is a shell, then inside the shell, anywhere, the contribution of the shell to the gravitational field is equal to 0. By the way, whatever arguments I am giving today in the case of the gravitational field, the same arguments will follow in the case of the electric field in electrostatics. So, for those students who know both the things, for them there has to be a comparison, and life becomes easier. So the mass of the inner sphere is equal to 4 by 3 pi r cube rho, which I can write like here. So, to the point mass here, it is only the contribution of the inner solid spherical mass, and so I can write that G at the depth d is equal to capital G 4 by 3 pi r minus d whole cube upon r minus d whole, into rho, divided by the distance r square, which is r minus d whole square. So naturally this square and over here they cancel, and what we get is capital D 4 by 3 pi r minus d into rho, and all I do is I scribble and substitute the value of rho in terms of the mass 4 by 3 pi r cube, and 4 by 3 pi they cancel, and then I get this Gm upon r, this I have to put as r square, not r2. Little dislocation makes it, and that is why our handwriting when we are doing mathematics should be more clear. Because look here, I just put it here and it became funny for me. So capital Gm upon r square, which is equal to small g, r minus d upon r, which becomes equal to 1 minus d over r. So the value of Gd turns out to be, now look here, I wind up here and take other things. Gd is equal to g 1 minus d over r, and the other result for the height above the surface of the earth that we got was g 1 minus 2h upon r. In both the cases, the value of d as well as the value of h is much smaller as compared to. Now what happens? Where is more fall? If the height and the depth they are the same, then you can see that the fall over here is more 1 minus 2h upon r than when we go deep inside it. Then if this is the variation is maybe here 2%, and the variation over here will be 1%, etc. So you have to give it a thought. I will not do the variation of small g with geographical locations, okay, but will rather deal in other aspects of gravitation, the escape velocity, for example, the satellites close to the earth, the satellites having a time period of 24 hours, everything, and how the escape velocity is the term that I used, but why it should be rather escape speed, that projectile leaves the influence of the earth and breaks away from that and goes further in space. So for that, again, this you question, we answer, you comment, we reply to your comment. Thank you very much. I enjoyed